Today we're going to be finishing up the last little bit of the week 8 slides that I put together for everyone. Gone through error propagation. We were talking about exponential functions. Gone through all of this. We were here at talking about compounding interest. So insofar as interest is concerned, we have two primary equations that we're going to be concerned with, or that we're going to be interested in looking at. Start off with, we've got interest that does not continuously compound. It compounds n times a year. So we're going to measure t to be, or we're going to represent rather, t to be years. T to be years. P is going to be the initial amount of a loan or a deposit. R is going to be the rate of interest, and N is going to be the number of times per year that lump sum of money incurs some amount of interest. This is, again, the formula for compounding interest n times a year. If, however, we compound interest continuously, we're going to have the equation A, the amount at the given moment, is equal to the initial amount times e raised to the RT. So n times and compounding continuously. Having said that, we had looked at this problem comparing two different interest rates, 7% and 11%, with compounding quarterly and compounding continuously. And we found that at a 7% rate, if we're compounding continuously, what will occur at the end of some time frame, in particular in this case 25 years, what we'll have as an amount is $69,000, blah, 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 $69,055.23. 7% quarterly is going to yield $68,017.87. 11% continuously is $187,711.58. And then quarterly at 11% is $180,869.67, or my mistake, and 0.07 cents. Wow, I can't talk today. So the point of this is to show that how compounding interest, continuously compounding interest versus n times compares to each other, as well as how interest rates compare to each other. So obviously, if we have a higher interest rate, more money will be incurred over time. And as n gets larger, more money will incur over time as well. And that's why, if you look at the quarterly compounding versus the continuously compounding, we find that continuous compounding interest incurs more money. Having said that, we're given this other example where we have to find the effective rate of interest compounding at a nominal rate of 6%. We want to find it for an annually compounding interest rate, quarterly, and a monthly. So what we need to know if I can find the slide somewhere in here. I might have accidentally deleted that slide when I was making this. Okay, what we need to know is that the formula for the effective rate of interest that's going to be REF. I'm trying to make sure I keep my notation the same as what the book uses. 1 plus R over N minus 1. So all of our notation is going to stay the same here. This is the interest rate, and this is the amount of time, or the number of times it compounds annually. So in our problem, we're given that R is equal to 6%. Well, this is going to be 0.06 as a decimal, right? In the first case, when we're looking at annual, N is equal to 1. In the second case, when we're looking at quarterly, B is equal, or N is equal to 4. And in the final case, C, it's monthly, so N is going to be 12. So I can erase this. We'll rewrite our equation up here. All right, so to solve for our effective rate in the first case, we're just going to plug 1 in for N. Excuse me. So all this is going to become is 0.06, right? It's just going to be 6%. In the second case, we're going to plug 4 in for N. Our R is going to stay the same. It's going to stay as 0.06. And I should write these answers as decimals, not as percentages. Now, I'm not going to pretend to know what this comes out to be, so I'm going to go ahead and cheat and look at what we have on the slide. It's going to come out to be 0.0614. And finally, we're going to have the case where it compounds monthly. So n is going to be 12. That's going to come out to be 0.62, oh no, 1.17. So the question here is, what is this effective rate? What does that represent? People at home, looking at what we've got on the board and the equation for an effective rate, what do y'all think this is measuring? If the people at home are talking, I can't hear y'all, and I don't know why. Somebody at home say something.
Amir, can you hear me?
A little bit, yeah. Awesome. All right. So, to answer my own question, what the effective rate is measuring is what you can expect to incur year to year, given how your interest rate is compounding, right? So let's look at what we've got here. We're saying that R effective is 1 plus R over N, all raised to the nth power minus 1. If we compare this to the amount that we incur over time, the difference here is we don't have t in our exponent, and we don't have an initial amount, right? So what this is measuring is the amount of interest increased minus 1 to tell us what the actual rate of yearly increase is. Does that make sense? I'm assuming that makes sense. All right, so moving on then. Well, actually, before I move on, I want to point out something else. Given that this is measuring what you can expect year to year as an interest rate, so the increase from this year to next year, then it makes sense that if you're compounding once a year, so annually, that the effective rate is going to be the same as the compounding rate. Make sense? It also makes sense that why your effective rate when you're compounding quarterly or monthly is higher. All we're talking about is comparing this year to next year, what percentage more will I owe or will I have, depending upon how this interest rate is being applied. So having said that, present value. Present value, how do I want to explain? Well, I'm just going to jump to the formula and explain it from there. Present value is solving for P, essentially. We have the amount we know how much we put in, right? Well, present value is up to this point, how much we put in, if that makes sense what I mean. So another way of saying it, another way of saying it is you get a CD, certificate deposit. And it has a particular interest rate associated with it, let's say 3.5%. That seems awfully high, but I'm going to say it. And we know that we want to pull out of this, we want to pull from our CD after 10 years. So T is going to be equal to 10. We know that our CD incurs interest rates, incurs interest, let's say monthly. So N is going to be 12. And we're getting this CD so that we can pay off a house down the road. We have an idea of how much we want to pay, let's say $100,000. So I have all of this in mind. The bank tells me the CD incurs an interest rate, like I said, of 3.5%. We want the CD to mature over a period of 10 years, to incur interest monthly, and we want the final amount on our CD to be $100,000. What we don't know is how much money we need to put down on the CD. How much money are we going to pay into it? That is what the present value is going to tell us. The present value says, all right, you want $100,000, you want it to compound monthly over 10 years at a rate of 3.5%. How much are you going to pay right now for your CD? Does that make sense what I mean? So we would say, cool, the present amount is going to be A in our numerator divided by 1 plus R 3.5, my mistake, 0.035 divided by 12, all raised to 12 times 10. Now I'm going to be real with y'all. I don't know what that number is going to come out to be. We could calculate it really quick and find out. But this is what it allows us to answer these types of questions. So looking forward, what do I need to do right here, right now? Cool. Having said that, awesome, perfect, a CD example. So we've got a 12-year certificate of deposit. Pays an annual percentage rate of 8% compounded monthly. We want to obtain a balance of 15K. All right, so in our example, numbers change a little bit. $15,000 at maturity. We said monthly over a period of 12 years. at 8%. So how much do we need to put in right here, right now? That's what we're asking. Having said that, it's going to come out to be P is equal to 15,000 divided by 1 plus 0.08 divided by 12 times 12 squared, so 144. Again, I have no clue what that number is, so I'm going to jump ahead. That means today, if we want in 10 years, in 12 years, our CD to be worth 15 or to pay out $15,000, right here, right now, based on this information, we need to put in $5,761.72. $761.72. So to answer the ever-present question of why do I care? You care because you can make some money right now. Granted, 15K is not a whole lot. And 12 years is a long time to wait for 15K. But you can make some money. So having said that, that is the end of this section. Yeah, I know I can't. All right, so where's my lectures? Right there. Having said that, we are going to peer into a little bit of next week, and then I am going to open up for questions and review. All right, so next week is all about chapter 4 stuff. Go figure, we're in chapter 4. We're going to start off with 4.3. I'm apparently dyslexic or developed dyslexia last night when I was making these slides. So I misarranged 4.4, but whatever, it happens. What this section 4.3 is going to be all about is the derivative of exponential functions. In particular, the function e to the x. And just like with the other derivative formulas or rules, we're going to prove this first. The proof of this is actually pretty straightforward. The first thing we need to observe is that the limit as delta x approaches 0, 1 plus 1 over delta x to the delta x. My mistake, I wrote that backwards. So there's two different formulas, one to infinity, one to 0. And that's what I just flipped in my head. Delta x, 1 over delta x. This thing's going to be equal to e. And that makes sense, right? Because last class, we saw that the limit as x approaches 0 of 1 plus x over 1 to the x, this thing's equal to e. Same idea. Except now we're using delta x up here. So having said that, setting our function equal to e, or equal to e to the x, we're going to find that our first term in the numerator comes out to be e to the x plus delta x minus e to the x, all divided by, of course, delta x. Well, we just talked about properties of exponents. In this first term, e to the x plus delta x, because of these properties, we know we can rewrite as e to the x times e to the delta x. So in our numerator, we can factor out an e to the x. And when we do, we're going to get e to the x times the quantity e to the delta x minus 1. Now here's the thing about this e to the delta x. And the thing we have to remember about limits. So in the past, I've already talked about how the limit as delta x goes to 0 of delta x is equal to d to the x. It's not actually 0, it's just something really, really close to 0. So close we call it the infinitesimal. We're going to use a similar idea here. Here we're going to say, hey, e to the delta x, well, this is going to be pretty close to e to the 0, but it's not going to quite be e to the 0. No, it's going to be e to the 0 plus something small. Should call it delta, but doesn't matter. Well, if that's the case, this is going to be like something like 1 plus another small number. Well, hey, we said delta x in that limit was something small, right? So when we apply the limit, is about that. And now the whole reason why this is because what the limit actually does. It's not 110% accurate to say it this way, but it builds an intuition across of what we're doing. We're saying this delta x thing, it gets blah, blah, blah. It gets small. It's going to get close to 0. It's going to approach it. When that happens, this e, well, it's going to get close to 1 plus something small, plus or minus something small. Well, delta x is something small, so why don't we just go ahead and call it that? Make sense? Cool. So using this sort of a logic, we're going to replace this e to the delta x with 1 plus delta x. And when we do, we're going to get that these 1's cancel out. We're left with e to the x times delta x, all divided by delta x, with the limit imposed. Well, that means all that's left is e to the x. Delta x is going to 0. So the derivative of this function is itself. This is why e is important. It is one of the only functions we know of that this is true for. Which makes it kind of dope, actually, kind of rad. Brings us to the rule about how to differentiate e to the x. Now, notice I kind of cheated up here. I just wrote x, right? What if, instead of x, we had another function, u of x? Then this thing, the derivative of it, would come out to be e to that function of x times the derivative of that function of x. Make sense? People at home, if you're nodding, I really can't see y'all through the blank screens.
Doesn't make sense.
Awesome, dope. Now, actually, before I get on into everything else that comes up next, I want to really quickly ask, y'all know what the word exponential means? What do you think it means?
So continuously increasing at a faster rate.
Not quite, but almost. The word exponential means that its next state is proportional to its current state. So it grows at a rate proportional to its current state. So for example, bunnies have babies in pairs, right? So one bunny leads to two bunnies. Two bunnies lead to four bunnies. Let's say we do this a whole bunch, n number of times. This is an example of an exponential problem. Because in the first case, we have one bunny. That's equal to 2 to the 0. In the second case, we have two bunnies. That's equal to 2 to the first. In the third case, we would have four bunnies. That's equal to 2 to the second. And in the nth case, we would have 2 to the n minus 1 bunnies. Depending upon how you want to iterate this. If you want to say that you're starting at 0, or rather starting at 1, then you have this. If you're starting at 0, then it would be just 2 to the n. But that's neither here nor there. So notice what's happening here. Every time what happens next is proportional by a factor of 2 to what happened previously. This is an example of what the word exponential actually means. I point this out because it's regularly misused. People all the time will be like, oh, it grows exponentially. No, it grows fast is what you mean to say. Exponentially means that its rate of growth is proportional to its previous states. So having said that, getting that math right out of the way, let's consider this problem here, this example. we're asked to find the slope of the tangent lines to our function e to the x at the points 0, 1 and 1e. So we're going to take the derivative. We're going to plug in 0. We're going to find that the slope is just equal to 1. We're going to do the same thing, but this time plug in 1 and find that the slope is just equal to e. In other words, if you were to take, let me erase this. If you were to take the graph of e to the x, this is our point 0, 1. Let's pick a random point on this graph. Let's call it xy. We know y is equal to e to the x, so we could rewrite it as e to the x. Well, the tangent line has a slope equal to the derivative at whatever the x value of the point is, right? So what that tells us then is that the functional value of e to the x is equal to the slope of the function at that point. Make sense? If you think about it, this is actually kind of cool. There's a lot of different ways you could interpret it, but the most straightforward way is to say that just that the derivative of the function is itself, and that is in and of itself kind of incredible. Especially since this number e just comes out of nowhere. So having said all of that, let's consider these examples up here. We're asked to differentiate each of these functions. The first case, we have e to the 2x. Well, we know the rule. For differentiating e to the ux, right? This thing's going to come out to be so if our function is equal to e to the 2x, its derivative is going to be equal to e to the 2x times 2. Now let's crank up the heat a little bit. Looking at g of the x, g of the x, is equal to e to the negative 3x squared its derivative is going to be e to the negative 3x squared times negative 6x. and so forth and so on. We can keep doing this forever, but I think the point's been made. So what about these different cases now? I want y'all to work on D, and I'm going to work on B and C. So for those of y'all at home who can't see, this is slide 7. Oh, never mind, it's not posted. So I want y'all to work on D. D is x e to the x minus e to the x. I want y'all at home to work on this while I work on B and C. You know what? I'm going to throw A up here too. So looking at these answers really quick and checking all of our work. For A, I got x e to the x plus e to the x, right? I just wrote it backwards. B is e to the x plus e to the negative x all over 2. C is x e to the x minus e to the x all over x squared. Notice they factored out an e to the x here. How about y'all? What do y'all get for D? Did anybody get x e to the x for D? Well, let's look at how this is done, right? I'm going to go ahead and erase this. That's all this is on slides. So we got our function f of x is equal to x e to the x minus e to the x. Well, we can go ahead and factor out an e to the x here. Minus 1. Now we're gonna have to apply the product rule, right? Well, what's the derivative of this? Just gonna be 1, right? So we're going to have that f prime of x is going to be equal to e to the x times d dx of x plus 1 plus derivative of e to the x is e to the x, so let's just go ahead and leave it as it is. My mistake, these are minus, not pluses. So the derivative of this is just going to be e to the x, 1 plus, we can factor this e to the x through, we're going to get plus x e to the x minus e to the x. And lo and behold, this is going to cancel with that. So all we're left with is x e to the x. So having said that, we got another example here. For those who don't know, a catenary is kind of a U-shaped curve. Honestly, I think I've only ever heard it used as a word like 3 times in my entire life, other than in this class. It's not a shape that shows up a whole bunch as the focus of a problem. But here we are, we find ourselves with it as the focus of a problem. So let's work with this thing. We've got that there are telephone lines, telephone poles, with lines hung up between them. They make this sort of shape. In our case, we're going to say that this, let me use a different color. This could be modeled with a function f of x is equal to 30 e to the x over 60 plus e to the negative x over 60. And we're going to restrain ourselves to the interval inclusive, negative 30 to 30. And what this is modeling is the droop of a power line between poles that are 60 feet apart. So this is modeling the y position, right? So we're thinking of this as a graph, sort of. We're moving x across, y up and down. So what this thing is modeling is going to be the position in which we can find our power line given some position along x. The height we can find our power line. Having said that, they're saying that this is 0, 0. And this is 0, 30. So just to kind of help us see what this picture is even talking about, or what this problem is even talking about. Now, I've already given it away, but we want to show that the lowest point on the wire is midway between the two poles. And we want to find out how much it sags at that point. I did do that one, didn't I? It is 60. It's 1 plus 1 times 30. So again, another picture of what we're looking at. A much better picture than mine. If you just shook your head and agreed with that, I'm failing you. So what we're going to do, since we want to find the minimum here, right? We're going to apply the derivative test. We're going to find the first derivative, set it equal to 0. Bada bing, bada boom, we got our x value, our critical point, right? So taking the derivative of this thing, I'm going to erase all of this now. Taking the derivative of this, excuse me. Well, first, notice we can rewrite our function, right? We can distribute the 30 through and make things a little bit easier on ourselves. Now, taking the derivative, it's going to come out to be 30 times e to the x times 1 over 60. E to the x over 60, I mean to say. Right? Plus 30 e to the negative x over 60 times the dx of negative x over 60. So this is going to reduce. We're going to get 30. You can factor out, well, we'll deal with that later. We're going to get 30 x over 60 times 1 over 60 minus 30 e to the negative x over 60 times 1 over 60 . So we're going to have 1/2 e to the x over 60 minus 1/2 e to the negative x over 60, or 1/2 e to the x over 60 minus e to the negative x over 60. Right? Same idea. So I'm going to go ahead and just clean the board up some. because all the work is up on the slide here. We're going to set the derivative equal to 0. Notice when we do, we can multiply both sides by 2 to get rid of our 1/2. Make sense? When we do that, we're going to end up with e to the x over 60 minus e to the negative x over 60 is equal to 0. We're going to add e to the x to both sides. Now we're going to make an observation. The only way these two things are going to be equal is if their exponents are equal, right? So this tells us then that x over 60 has to be equal to negative x over 60. So we can multiply both sides by 60. And we get x is equal to negative x then. But that never happens unless x is equal to 0. So our critical point has to be x at 0, right? So now we go back to our original equation. We put in 0, and we calculate what the height is. And then if we want to know what the height is at the two poles, we can calculate those as well, because they're our endpoints, right? So if we want to find the droop's going to be the difference between our highest peak and our lowest peaks, right? And that's that. Having said that, how many more slides do I have? Not many, okay. Having said that, I'm going to stop here and let y'all ask any questions you may have about the exam.